Welcome everyone, welcome to ECTQG and in particular this session on scaling laws and urban form. My name is Harry Odell, I'm a PhD student here at Manchester and I'll be with you today on the Zoom call, so any issues just drop me a line on the chat and we can see if we can sort that out for you. Just quickly, a couple of housekeeping things before we get started. Please, and I'm sure we're all familiar by now, please keep muted throughout. Participants are going to have 18 minutes per session. I will give you a warning with 5 minutes left and 1 minute left. We're trying to keep to a relatively strict timetable, so I do apologize for that. And last thing is the questions, please keep them, jot them down, and then after all participants have talked, there will be a session for discussion at the end. We'll open it up to you guys, and then hopefully we can have a discussion around the talks we've had. It's now 2:30. Numbers have just crept up a little bit, but they're fairly stabilized. So I think we'll crack on and get started. First speaker today is Raphael Bublos. So I saw you were here before. I invite you to share your screen. Very much looking forward to the talk. He'll be talking today on convolutional neural networks for building types classification in Switzerland. So by all means, welcome Raphael and get started.
Okay, thank you for the introduction. So my name is Raphael Bublo. I'm a PhD student at the University of Lausanne in Switzerland. And as said, I'm going to talk about building types classification in Switzerland using convolutional neural networks, or as they are called, CNNs. Here is the outline of the talk. So first a brief introduction, then some theoretical and technical detail bases, some methodological considerations, tiny early results, and conclusion discussing the current difficulties I encountered and consecutive research prospects that I have. So the main objective of this research is to obtain a model sufficiently accurate to predict a building class or category. To reach this objective, we use nationwide available data of two-dimensional and three-dimensional geometries, plus some registry information to build a new data set looking like an image repository. The next step is then to code and train deep learning neural networks on this new data and to compare the results of the different models to be able to select the best one. So this study could help determine if geometries of geographical objects are compatible with CNN's training. If predictive analysis is possible, then maybe generating geographical geometries according to labels could be the next step. So thanks to artificial intelligence and the increased aerial imagery availability, the global coverage of buildings' footprint continues to expand every day. However, data about buildings type or functions remain quite sporadic or is detained by the authorities, generally the local authorities. Due to the benefits, some of them listed below, of knowing types and functions, different research have taken to building clustering or classification. Here's an arbitrary selection of researches on the topic. So for example, in the first one, morphology and density indices were computed and several data reduction and classification algorithms tested to find urban structures suitable for map making. In the second, features were computed at several scales: the building, the block, the neighborhood, the municipalities, before being clustered in similar groups, such as for buildings, for example, linear housing, large-scale building, or multiple wings building. And in the final studies listed here, they used raster and vector data, footprint data, to assess the potential of automatic type classification and the most appropriate data input. So to summarize, the studies about buildings tend to vary with regards to the data, the methods, or the scales. Some work, for example, on individual footprints, some on aggregated ones. The definitions of type and function change with the data sources, so they tend to change also country by country. And the building morphology is considered also with external information such as land use or points of interest. And now we have finished with the building classification approach. We can move on to CNNs. So CNNs are a class of neural networks that are used for to analyze images using a lot of labeled data. They make use of convolutional layers, which we can say is a way of applying different filters on images. And the result of these filters are then activated or not in the neurons, and with each epoch, they are refined. And with multiple passes of each images, the model is able to predict an output or a class probability. So in this example, I have a picture of my cat that I give to the model. It will be passed through layers which are typically found in the CNNs. Convolution layers are where the filters are learned and activated. Pooling layers are where the image height and width is reduced. And dense layer are generally at the end. There are a set of interconnected neurons just before the classification. So here, if I give a picture of my cat, it will give me a classification, a probability of being a cat, a dog, or for example, a rat. So I'll just try and switch to this live model in running the browser from an example from a class in Stanford. Here you can see on the left the input. There is the first convolutional layer, the activation, then one more convolution activation, and a pooling layer. This is repeated 3 times. And at the end, there is the fully connected layer, and gives you an example of the probabilities at the end. So generally, they are repeating in the architecture, they are repeating convolution and pooling layers, and at the end, the dense connected. But some of the new architecture don't use pooling layers anymore. CNNs have long been used, and building classification is no exception for the use. So in the first study listed here, there's a great overview of a lot of methods and applications. The second one, they used street level imagery to classify building for finer land use mapping. And in the last one, they also use Google Street View, but they fused it with aerial imagery to obtain also better land use classification. All of this was in the US. And so let's move back to Switzerland. Here on this building map of Switzerland, you may see that we have a territory of urbanized plains, and except for the valleys, we have some unoccupied mountains. And surprisingly, most of the people, around 3/4 of them, live in the cities, in buildings. And these buildings, they are available as 3D geometries for the whole country. As you can see below, the models have a ground surface, facades, and roofs that correspond to the LOD2 in city GML specifications. Small buildings under 24 square meters, for example, are generally not included. As all Swiss Topo data since March, all of that is freely available online. So I can only recommend that you go and check it. For the label data, they are found in the National Register of Buildings and Dwellings, which is managed by another agency, the National Statistical Office of Switzerland. It exists since 2000, but as it has become a central piece of Switzerland's energetic strategy, the exactitude of the data has greatly improved in the last years. There is information about everything building related, with plenty of characteristics surveyed. The Federal Statistical Office uses 6 categories. 6 categories based on the general usage of the building. Here, for example, the category other residential building englobes the complexes of flats with shop at street level. They also have classes, 25 of them. So here, here I grouped them by colors. For example, green are all classes in the residential housing superclass, and each shade of the same color, for example, here in the light green, is a superclass. For example, here the multi-dwellings. As you can see, some classes are highly specific, such as bars in non-housing buildings, and others are quite fuzzy, like the rest, other not classed anywhere. Some of the superclasses also mix building we wouldn't maybe put together, such as a hospital with religious buildings. And the last data we used was issued from OpenStreetMap, which is a database of geographic objects, collaborative database. And we extracted the buildings and roads according to the tags shown below. So now we have seen the data, so we can have a greater idea of the process used. First, we had to join the building dataset because they are managed by different agencies, so they don't have a one-to-one correspondence. It is supposed to come sooner or later. So the registry data was plotted using X and Y coordinates. And for the 3D buildings, the Z coordinate was ignored, so we would get a footprint. When there was a one-on-one correspondence, the category was assigned. When there was no correspondence, the building was discarded. In case of multiple correspondences, it was only assigned if the categories or classes matched. The 3D data is represented by triangular meshes, and they represent the surfaces. So in order to transform that into 2D, we had first to lay a grid center on the building. Then for each pixel center, compute a 3D line going through the building and assign the delta between the intersection of the line on the roof and in the ground as the value of the height of the building at this particular pixel. This gives a matrix like this that we pad with zeros around to obtain the standard dimension. As we have seen, CNNs use multiple channels, use images which have multiple channels, such as here on the left 3 channels, but they can have more. So in our case, we have 2 more channels. We can leave them blank, duplicate the first channel, or employ more data. We decided to incorporate data corresponding to the surroundings of the buildings by keeping the same matrix size, but changing the resolution of the raster to have a bigger look at what happens, what is located around the building. So each data point in the final data sets consists of an image of these 3 channels, and to each image is attached a label. So now on to the very early results. We started to experiment with the CNNs using the categories. So we have 5 categories because the temporary housing was discarded. As you can see, due to the nature of the dataset, the categories are not balanced because there is a majority of building exclusively dedicated to housing, for example. The dataset was divided in training, validating, and testing sets representing 80, 10, and 10% of the total images. So it is a really early result, and there's a lot more to come, I hope. So using a ResNet 50 architecture, it was possible to obtain an global accuracy of around 65 to 68%, which is better than just picking one of the 5 categories at random. But it's not really the best result possible because due to imbalance, while the first class represents the 75% of the total images. So if you put all prediction in this class, you will have a 75% accuracy, which is better, but is not right in itself. So there's plenty of trials and errors still to be made. And there are also some points that already require attention. So as you saw, due to the nature of the datasets, the classes are heavily imbalanced. So we have to use strategy to counter this imbalance, such as over/under sampling, maybe trying to use different percentage in the validating dataset, maybe give more importance to the main category or not. And we also have to change the way we evaluate the performance of the model, due to this fact that we can maybe shift all prediction into one class and it will give a better overall accuracy, but it's not a real better overall accuracy. There is also the fact that the dataset is generated automatically. So maybe the rules can be improved, but there is also a lot of inertia due to the size and the computation time needed for the calculation of the dataset. So if I just want to change the resolution of one of the channel, I need to recompute all information on all buildings of Switzerland, which is really time consuming. And I cannot also exclude that on the more than 2 million data points that exist in the registry, there aren't any garbage in. So I may have garbage out because all the data is inputted at the municipality level and is then controlled at the national level. So it may have some incoherence in it. One of the one I saw that marked most was the Lausanne Cathedral was marked as other building and not in the religious building, for example. And also there are a lot of CNN architectures, different architectures using different layers, and tuning hyperparameters is not that easy. So sometimes it's quite hard to know when you have more to gain from an architecture, or when you should simply leave it and try another model with less or more layers, for example. But it is said to come with the experience. And then the future works, maybe try to work on more homogeneous regions. As I saw in the previous studies, for example, in Germany, models were better performing when they were on the specific region, such as Bavaria, and they didn't scale well when taken in the whole country. So maybe it's the case in Switzerland, as we have seen. It's maybe harder to predict the class or category of a building isolated in the mountains compared to one that is in the city. I also want to try to maybe incorporate mixed data. So using, for example, the year a building was built, to filter all those buildings and have a mean building style, or maybe use the filter used by the computed and learned by the CNN to see what really distinguishes a building class from another. And finally, what interests me a lot is using generative adversarial networks, or GANs, to generate a possible building landscape future for Swiss municipalities, which follows planning laws and needs in terms of infrastructure. That's it for me. I'm updating my GitHub gently, and do not hesitate to contact me if you have any questions, remarks, or suggestions.
Perfect. Thank you very much. Sounds like a very difficult problem, but you're making what seems like good progress with it. I'd like to invite the next speaker up now. Remember, save questions for Raphael until the discussion section at the end. The next speaker today, just two, not quite sure which one will present me, is Roger Vasquez and Roberto Pons Lopez. They have a presentation titled "A Data-Driven Methodology to Identify Urban Form and Characterize its Functionality." So if you'd like to share your screen recording, and feel free to start whenever.
Thanks. So thanks everyone for joining this presentation. My name is Roger Vasquez. I will be walking you through this process that we are currently working on, which as we go through this deck, is going to showcase a methodology in which we can try to identify specific regions, functional zones within a determined area of study. So about the authors, Roberto Ponce Lopez is a PhD in Urban Information Systems. He's a professor at the School of Government and Public Transformation at Tecnológico Monterrey. Myself, Roger Vasquez, I'm a bachelor in Computer Science and Technology Engineering. I'm currently doing a minor in Intelligent Systems, and I work with Roberto as his research assistant. The agenda for today's meeting, hopefully this will be going smoothly. Are 4 basic steps. First, the overview, the objectives of the description of the project at glance. Second, ADV scan, which is an algorithm we use at the project. Third, the topic modeling algorithms that we use, the description and parameterization of each one. And finally, the results. So first one, for just as a quick reminder, functional zones are a byproduct of urban development. They appear on cities based on determined beforehand planning, or maybe sometimes sporadically due to the growth and urbanization of zone. They host a range of needs for its inhabitants, whether it be schools, commerce, industry, workplaces. So an example of a functional zone may be an industrial park within a city that has been, placed there with specific reason because of public policy. And these zones help us to identify the structure of the city and its underlying interactions, meaning that, for example, certain persons from a determined zone, which is used for housing, may have a relationship with a zone that's used mostly for workplaces, be it industry workplaces or maybe office workplaces. Currently, there are several ways of identifying automatically functional zones, but one of the most used methods is what we are going to discuss here in this slide about state of the art. So these papers that are the quote that are cited in the left lower corner have different pre-process and post-processing approaches, but generally can be resumed in 3 steps. So first, they split the area of study based on main roads and known areas that have relevance to the process. Then they select the points. So this, how they do this is they first select mostly main roads, avenues, or maybe they know beforehand that a certain area in the area of study has some relevance to the project. For example, as I said before, an industrial zone that has been planned. And then they select the resultant segments, the points within the resultant segment. And these points can come from different sources, such as private or public databases containing points of interest, for example, OpenStreetMap, or maybe some context-based data from social networks, for example, tweets, or maybe data from sources like Foursquare and maybe Yelp too. Which contain the names of restaurants and museums and other places of relevance within a city. Then, having these points, they get labels from it, and they apply a topic model algorithm to them. And the general idea behind applying the topic model algorithm is to find the distribution of points within the zones that they are working on. So, a topic model algorithm purpose is to find exactly a distribution of words which are get from the labels, and in some way this is a parallel of finding functionality of the zone, as we are going to look in the next steps. So the first thing that we did was to define an approach in which we could generate documents or areas, and we decided to choose a density-based approach. Because most workplaces and economic areas in the city are density-based and they're not randomly placed alongside the rest of the study. So they're mostly on a dense basis in certain specific points. for any given reasons. So the algorithm that we choose for this process is called approximate DB scan, which is an ensemble of DB scan. So the general idea behind this algorithm is to apply the DB scan algorithm to a random subset of the data set with a given size. In this example, we use 10% of the whole data set. Then it repeats the process for a given number of iterations. In this example, we use 100 iterations and keeps only the most common solutions. So if a point is not present in at least a given threshold value, for example, 8% of the solutions, it's considered noise. And this approach gives us the facility of having a built-in stability metric to monitor how good our final solutions are. So the ADB scan algorithm was conceived especially for geographical information system purposes. And the image to the right, we can see it's an image from the paper of the authors, in which they generate the stability index and the boundaries for different metropolitan areas in Spain. And applying this algorithm to the data set, which I forgot to mention, is the data set collected by the National Institute of Geographic and Statistics at Mexico, which contains all the registered workplaces in Mexico in the way in georeference manner, having the latitude and longitude and all related variables to the economic activity. So we apply that algorithm to that data set in the metropolitan area of Monterrey, which was nearly 107,000 points of interest, and we got 66 clusters, which covered with nearly 40% of the data set covered in our clusters. Having our clusters formed, we select each cluster as a document, and we take the label of each point of interest afterwards. So in this data set, the NUE data set, you can find on the internet in the page of the National Institute of Geographic and Statistics, but sadly it's only in Spanish, I think. It uses a nomenclature called NAICS, and NAICS is a hierarchical nomenclature which contains a description of the activity of each economic activity, from very specific to not so specific. And we chose a midway along that range. So for example, the labels that we are working with are things like retail, drink size, and tobacco, which describes minor businesses that provide minor retail services of drink size and tobacco, insurance, bonds, and retirement funds companies, along governmental activities, and so on and so forth. And this, the graph, the chart to the right that we can see the number of work distribution in each cluster. The cluster number 2, which is the cluster at the downtown Monterrey area, is the one that has a lot for representation because it has several points of interest within it. And then the idea of taking each cluster and taking the words of each point of interest within the cluster is to build documents. So topical model algorithms are meant to find the topic distribution within a set of documents. And there are different approaches to it. And we select the showcase that we are making here is the latent direct allocation algorithm, which the general idea of it is that it takes each word, select each specific word within the set of documents, creates a vocabulary, and using a back and forwards approach, finds the distribution within the frequency of words within a set of documents. So at the end, what you have is a topic distribution that shows, for example, how probable is a certain topic to pertain to a specific document. And the results behind that are shown in this map. So for example, here, the orange areas represent highly mixed areas of economic activities that have, for example, things ranging from industry, museums, entertainment centers, and also restaurants, minor retail, but also retail in bulk. And on the contrary, for example, the lighter brown subcenters have mostly specialized and technical knowledge economic activities, such as financial activities, consultancy services, IT companies, and so on. And I think I forgot to mention is that the general idea behind this work was to take each of these already documented and proven techniques, and select the most interesting part or the most important parts from each of them and build a standardized process that could be replicated for several other purposes. So in our example, we built this process, this data set, this areas, this segmentation to complement an analysis that is going to be done on economic segregation and crime analysis within the same area of study. So our hope is to have at the end a prescriptive approach that will serve researchers at glance to possibly complement their data sets and identify functional zones within areas of study. And regarding the next steps in this process, we want to replicate this process on other areas of study in Mexico with the same data set, and also to exemplify the ways that this process can be applied and can be used, and the usefulness of it in general, but also to have a way of generalizing things like the parameterization of the topic models algorithms. So right now we are using topic coherence metrics, and we are only selecting the topic with the highest probability of pertaining to a certain document, but we want in the future also to explore ways of distributing these topic assignments using maybe another clustering algorithm within this. So yeah, that'd be all from my end. If there are any questions, these are our contact ways, both LinkedIn and the institutional email. Thanks.
Thank you, Roger. Another interesting talk. Well ahead of schedule at the minute, but again, we'll hold back on questions to open the floor to everybody. I'd like to invite the next speaker, Paul Kilgarriff, co-authored with Remy Lemoy and Geoffrey Caruso. I know, Paul, you've been having some problems. I hope you're able to.
Yeah, I can. Hopefully, you can see the screen now.
Yeah, perfect. Got it. By all means, take it away.
Can you see that now? Is that just the slides?
Yeah, that's just the slides. Yeah.
Yeah. Okay. So what I'm going to talk about today is a new city definition using a radial homothetic scaling law as well. And this is some research I've done with Remy Lemoy and Geoffrey Caruso. And this is from a project which was funded by the FNR Core in Luxembourg. So just a brief outline of the presentation. So why do we need another city definition or city definition method? Well, we need I suppose one of the motivations behind this was to come up with a universally applicable method, and one which only requires population grid and kind of minimum data inputs. This method also allows us then to align population and spatial extent, so to identify the fringe distance of a city in a possibly more accurate way. In terms of methodology, we use radial analysis and scaling, so building on existing research, and then a homothetic scaling law to allow us to compare cities of different sizes. We also make use then of a convergence process, which will arrive on a converged population for a city which will match its extent, and then identify optimum weightings and densities by the total population, and also then to improve on existing scaling methods by moving away from using functional urban area populations as a representation of the city population. So in terms of city definition, I suppose what is meant by a city? Is it to include the urban core, suburbs and periphery, or maybe a broader sphere of influence of the city? In terms of the research, we take a monocentric approach of cities, or monocentric view that even within a kind of polycentric style city, there will be a dominant core which kind of dominates the surrounding subcenters. So Mounier pointed out that a definition should be universal and common to all cities among all regions and should be uniform everywhere. So existing methods typically use local administrative units. However, you have inconsistencies in size and scale across regions and countries, and also then issues in terms of bias, such as the modifiable areal unit problem. But then there's also approaches which use a functional approach using commuting data. It's an improved fit. However, there can be a lack of commuting data in a lot of regions, particularly in the developing world. So this new approach will use, it uses a continuous definition and rescale distance thresholds to arrive at a converged population for a city. So it's distance based, so it's based upon the kind of the historic or this idea that one of the most important factors in terms of residential location is distance to a major center. So in terms of the scaling methodology, we use the scaling which was found by Lemoine Crusoe, found that cities scale in a homothetic way. So if we use the example of the cubes here, the volume of the cube will scale proportionately to the side of the square, in which case we can relate the size of cities are proportional to each other. This is based upon kind of historical work which looked at animals in terms of how they scale in terms of body shape and size. So population density then is proportional to the cube root of total population. And what that means then in practice is that the Lemoine Crusoe found that the radial distance of a city is proportional to the population of the largest city, which in this case is Paris, over the population of the city in question. And it's a cube root law. So this is where we find the scaling factor, which is k in this case. So r times the scaling factor will give us the rescaled distance. So for London and Paris, because they're large cities, the rescaled distance will be the actual distance. For smaller cities, it'll vary. In terms of data then and methods, we use Urban Atlas data from the EU Copernicus. So this is available at a 5-meter spatial resolution, and it covers the larger urban zone of cities, or the functional urban areas as they're called now. And we use this then to produce radial profiles for 540 cities. To this then we link the Geostat 2011 data, which is at a 1 kilometer grid cell, and we attribute population to 20-meter land use cells weighting by the land use. So this then gives us a radial analysis of population. So at each ring, a ring then is measured as a function of distance to the center. Within each ring, we know the population that lives within that ring, and we can create a profile of population density, or a profile of population. In terms of the city center point, then we use the city hall as the focal point, and this kind of corresponds with previous findings and results. So in terms of the procedure then used to calculate the new urban extent, we start off with the starting point of the population of the functional urban area. We then calculate a scaling factor for each city. So this is used based upon the population of the FUA of a city, and then the population of the largest city, Paris. And we then rescale each distance from 1 to 100 kilometers. And in this is just an example of, say if we were to look at a rescale distance of 40 kilometers. So we take the population of the FUA and calculate the scaling factor. We then rescale each distance. We cut at the rescale distance 40 kilometers and record the cumulative population. We then recalculate the scaling factor again and repeat steps 2, 3, and 4. We then, after typically 4 to 5 iterations, the city will converge on a population. we just carry out 15 iterations, in which case we know that for sure for most cities we will have a converged on a population. And this procedure then is repeated for every distance from 1 to 100 kilometers for all 540 cities. So in terms of sensitivity analysis, to look at what is the most optimum distance at which to cut cities. So the results here show the difference between, so distance R prime, and we compare the sum of square differences between R prime and R prime plus 1. So the difference between the population at 60 kilometers, how that differs to the population at 61 kilometers, and look at the difference. And this then is the sum of the square differences for all cities. And we can see that as we move towards the 0, the overall sum of square differences is decreasing as we're converging on a population. And in terms of, this will probably show it more clearly in terms of the optimum distance. So taking all the sum of square differences for all cities, we can see that as we converge towards 0, the optimum distance at which to cut cities is around 31 kilometers rescaled. So we use this then to define our new cities. So this is used as to represent the new definition or fringe distance of cities. So it'll be 31 kilometers rescaled. So just some comparison with existing definitions. So the 4 definitions I consider, the Urban Atlas have urban centers, EU OECD urban centers. So these are based upon density above a threshold and then a minimum threshold population. The FUA boundary then is based on at least 15% of commuters in an area, in a LAU commuting to the urban center. The GHSL then, it's got a similar methodology, except it adds 50% built up surface criteria. And then the FUA is similar again, except that it ensures there's no overlap. So in terms of how the new definition compares, we can see that overall it's slightly larger in extent compared to the core, Urban Atlas core and the GHSL core, and then not quite as large as the functional urban areas, with the exception of a few outliers. And we can see here if we look at the ranks of the 2 measures, so Urban Atlas FUA and then our new definition at 31 kilometers, we can see that by and large, the difference in ranks is in between 10 to 50 places. However, there's a few exceptions, which I'll talk about later, which are cities located in urban agglomeration regions. So what it looks like on a map, we have Berlin here on the left. So the blue is the current Urban Atlas FUA, so it's quite large in extent. It's 100 kilometers wide across, and the core then is a lot smaller. But we can see our rescaled definition, 31 kilometers, slightly larger. So it covers the urban core and parts of the suburbs as well, possibly even the suburbs. In terms of Barcelona, we see again, so the Barcelona FUA is slightly more compact, and our rescaled 31 kilometers. So the CBD would be probably about there in the center of the circle. We can see it covers a wider extent. So I took an area, the northwest around Manchester, Liverpool, Leeds, because it's quite an urbanized region, to show how this works, to show how it is efficient at converging on populations, even when there are nearby cities and clusters of populations. So the purple is 31 rescaled using the FUA population. So the convergence pop will be smaller, and you can see that for certain cities, we're converging tighter in a more compact area. So the circle for Leeds has converged more compared to the circle for Manchester. And in terms of how that compares to existing urban atlas regions, we can see that it's possibly more accurate to what defines a city in reality in terms of close proximity, rather than possibly out in the periphery, where it can be very difficult to discern whether a person is within the catchment of Leeds or Burnley. And just the same map again, just to show the population density. So you can see that it's fairly close around the areas with the highest levels of population, and also then includes some more kind of semi-populated areas or suburban regions. So in conclusion, using this method, we can identify the fringe distance in an efficient way. The convergence process is that it's a data-driven approach, as opposed to imposing too many restrictions and thresholds in how to define a city. The method requires very few pieces of information, so it can be applied to a wider geographical regions. The results show that it compares favorably with existing definitions, so larger than the urban core and possibly more compact and more accurate compared to the larger functional urban areas. So further steps will examine, without needing the starting FUA population, and further sensitivity analysis, and also then the issue of polycentricity. It was difficult to delineate some metropolitan areas such as the Rhine-Ruhr metro area. So maybe it might necessarily have to look at identifying where the main center is in these regions. So hopefully to contribute to the existing debate on what's a city and what's a sub-center. So thanks. Look forward to questions later.
Thanks, Paul. That's great. Yep, cheers. So last speaker of this session before we move on to our discussion and questions is from Gian Piero Lombardini. We talked about power law, scaling, and the degrowth geographies in the case of Italy. So if you're in the call.
Yes. Good afternoon. You can hear me? Yes?
Yes, perfect.
Well, is right.
Yeah, we can see that.
You can see the presentation.
Yeah.
Yeah. Good. Very good. Very good. So this contribution starts from the consideration that the ZIP law applied to urban systems makes it possible to evaluate both the degree of the economic maturity reached by a certain city system or a city system of a nation, and its degree of hierarchization and homogenization. The spatial distribution of populations and cities explained by power laws has normally been used to represent graph conditions, both in demographic and economic terms. In all those situations where territorial development phenomena have been recorded, the power law applied to population conditions has allowed us to grasp interesting allometric relationship between cities and urban systems. Well, the aim of the contribution is to better explain the Italian urban systems as an interesting case study, starting from rank size law and based the whole contribution on three hypotheses, theoretical hypotheses, considering Italy as a recent territorial assemblage of small and medium-sized kingdoms with a long history that have reached the unification resulting in consolidated and diversified urban hierarchical systems. The second hypothesis is that the development of industrial Italy is late and was conditioned by the evolution of different urban systems during the history, the urban history and territorial history of Italy. And the third hypothesis is to recognize the characteristic of urbanization process through a reformulation, a partial reformulation of the ZIP law that makes evident the characteristic features of the evolutionary history of the case. Well, the explanation power of power law is evident, and in some cases, ZIP law has been interpreted as the result of an accumulation process. In other cases, the power laws has been used to explain in a static or dynamic way the process of the city growth. And on the other hand, the imperfect adherence of empirical data to the simple equation, ZIP equation, log of the rank size relationships has led to study various problems, such as the problem of the form of distribution, a Pareto distribution or log normal distribution, for example, the problems of tails, the existence and explanatory power of generalized scale behavior. ZIP law explains the dynamics of urban systems in growth or in stationary economic equilibrium. But what happens for urban systems when we have a nation with a long urban history, as the case of Italy, of other European nations, and for who experience periods of stasis or degrowth that are differentiated both in time and in space. The long urban history of Italy explains its strong inertia to change in the urban hierarchy. Economic development tends to be conditioned in a path-dependent manner by the economic and social history of individual cities or city systems or city regions, and by the fixed capital accumulated over the course of a long term. The empirical data would seem to confirm, in the phases of strong economic and social growth, a tendency to maintain over time the Pareto distribution with normal higher exponent values in correspondence with the conditions of greater development. The question that arises, what happens when we are faced with situation of stasis or even degrowth? In the Italian case, that is a country that is entering in a phase of demographic stagnation, the same allometric relations that are recorded with a central constant irregularity in growth period are also maintained by empirical data evidence in the stabilization phases of urban systems. It is already been shown that while a certain general consistency is maintained in ZIP law in the history of urban systems, below this irregularity, great changes are actually observed with significant variations in the rank and economic importance of the individual cities. The development path of a city or a particular subset of cities within the Italian context can diverge from the more general path of economic growth, and in some cases present dramatic collapses in terms not only of population for some cities of the systems, but also for economic performance of cities itself. This factor would indicate that the general economic development can proceed in a special and equal way. Population and activities move the geographic space in the geographic space, creating even considerable territorial gaps. The attraction exerted by agglomeration economies often tends to create cumulative cyclical process to exclusive advantage of only a group of cities, for example, but at the same time to the disadvantage other cities. In Italy, we can observe, in fact, a general tendency, the creation of very large urban fields beyond the metropolitan area concept, in some cases without economic development, such as in some cases of meridional cities, Italian cities, such as Naples, Messina, or Palermo. Italy presents itself as an interesting case of territorial assemblage. Italy has reached unification only in recent times, and after a long process of unification that has seen the aggregation of a series of small and medium-sized states that had been independent for centuries. The unification process was in fact completed only after the First World War. So it can be said that the Italy we know today has little more than a century of life. Italy was then characterized by the process of late industrialization and urbanization processes, which affect different areas of the country unevenly. These starting and non-linear development processes have led to the emergence of significant territorial differences. Development processes have proven to be largely path-dependent. The same administrative management, for example, also in the administrative subdivision of territory, the boundaries of city administrative term, had to adapt to structures and traditions that have been around for centuries and are differentiated on a regional level. Morphological condition, general macro-territorial morphological condition have historically always been relevant in determining the development of urban systems in the various Italian macro-regions. Certain territorial conditions were decisive in creating the Italian urban systems. For example, insularity, the presence of two large mountain ranges that divide the space of the nation, the remarkable length of the peninsula, the presence of two seas separated by a mountain range, which determine two different views of the peninsula and the predominantly north-south direction of development of the city systems. The Italian urban networks are therefore the result of a long historical process that has led Italy to differentiate itself into separate regions. All have the dominant character of polycentrism. In some contexts, typical crystallarian landscapes can also be observed. The role of coast and natural ports has meant that some regions developed a thriving relationship with the outside world, which have been maintained over time and which constitute one of the legacies of history. The communications systems was strongly influenced itself by the geographical and morphological characteristics of territory. Further refinement of a research on the Italian urban system come from the application of a rank size estimation model specifically studied for this contribution in this occasion. The purpose of the research here was to carry out a cross-sectional analysis of the static type applied from time to time of 4-time threshold, 1921, 1951, 1981, and 2019. And that are significant date in the history of this century for Italy. Now, in our model of the rank size rule for Italy, instead of assuming the well-known log-log equation, it was decided by us, by researchers, to analyze the rank size relationship with a different equation that you can see in this slide, with a different equation. And that is the result of an algebraical inversion of the original equation log-log. The result, as the descriptive statistics of the estimator show, is better than obtained with a traditional logarithmic function. The graph of the traditional rank size equation show in the top of the page shows some predictive limits between observed and expected results in the two tails above all, and also in the central area, the area of medium-sized cities. Mean the estimate presented here here is based on a nonlinear equation on which an algebraic transformation has been made to bring it back to a linear form that allows us to estimate it with the OLS method. The model thus conceived moves within two limits. The first limit coincides with the case, obviously only hypothetical case, that the whole population of a nation is concentrated in a single large city, the vertical line here. And the second limit, on the other hand, represents the case of a perfect equidistribution in n cities, all of the same demographic size. And beta here tends instead to 0. Therefore, a growth of beta over time signals a trend towards urbanization in larger cities. The greater the beta, greater concentration in the major city represents. The comparison between the standard equation, the results of standard equation, and the expected and observed points show that the new model here proposed is better to estimate the observed data for all the 4 dates. In fact, the model shown here with 2019 here works well for the upper tail, while for small times, it seems to suggest a possible truncation of the representation of the data only for relatively few municipalities. Those are very small size. Well, there are other graphs, and so in conclusion, the Italian urbanization process show that the Italian population continues to be concentrated in the largest percentage in municipalities in large cities, but not in all large cities, but in those municipalities, above all, between 10,000 and 50,000 inhabitants. And this group of municipalities records a constant growth through all the century. So the rank dimension, the rank size rule applied to different regions, similar to original historic regions of Italian regions, is also valid in these regions, and show a more homogeneous and structured urban hierarchies. Here is the example of Tuscany, and for example, another example is Lombardy. In conclusion, Italy presents, analyzed by this model of rank size, presents a typical case of urbanization and a specific case of urbanization with a specific urban dynamics and of growth and the growth in any case. The trend of urbanization process over the last century, analysis through an estimate of rank size equation, demonstrates three typologies of city. Vital large cities that are often very dynamic and also drive the country economically, such as Milan, Turin, and the medium-sized city of the Po Valley and the Tuscany. Another categories, another typology is the other large cities, the large cities of the south of Italy, for example, that are demographically oversized with respect of their economies. And there are a third category is the medium-sized cities that is the very specific issue of the Italian urbanization, and the rural cities that are suffering a demographic crisis. Well, thank you.
Thank you very much. That concludes all the talks for this session. We're now going to open the discussion up to the floor. So any questions that you have for authors, please feel free to ask. I'm going to ask at first that we raise our hands just so it's a little bit structured and we can get through all the questions systematically. And then as we move more free flow, feel free to shout out. So yeah, questions for the authors, please. Denise, would you like to go first?
Yes, thank you. My question would be to Paul Kilgarif, and I think that he very well demonstrated that the method that the group proposed arrives to much better results than the application of a uniform density level as for limiting, for delineating the agglomeration. My question is about, did you check if the limit you determine could correspond as well to a change in the fractal dimension, the radial fractal dimension of the distribution of either population or built up within the urban area?
Thanks for your question, Denise. No, we haven't looked yet at fractal. I think that probably is something worth considering. Possibly as well to look at, we have data as well on the level of soil sealing. So that might be something as well to look at, and whether the distance, if it corresponds to perhaps a sharp drop off in the population density.
Yeah.
I think
my question is because it could it requires perhaps a different kind of information or less information, and if it is completely congruent, you can use in different cases of countries having different data to analyze. You can use either one or the other. Okay. But I'm glad that you think about tempting it.
Yes, thanks very much. Thank you.
Do we have any more hands? I don't see any now, or questions. Feel free just to shout out. No, nothing. I've got one question for Raphael. The first talk. I was just wondering about the use case of trying to do what you were trying to do, and second, within that, what would be a successful level of accuracy for you given the use case?
Yeah, it's a good question. Maybe I want to talk about the final end use. So the point now is really to assess whether using CNNs not on real images, if I can say so, but on images made using those geographical and geometrical data sets are viable or not. And if yes, it may open the door to further analysis. And the question of a satisfying accuracy is really a tough one, because as I said, it's really hard to compare between the several studies that have already been made, as they all use different definition of what is a building, what is the type of a building, what's the function of a building. Some have a larger categories such as public building, which englobes hospitals, universities, government buildings, libraries, and so on. And some try to have more precise categories, such as isolating hospitals, isolating research facilities, and so on. So what I saw in the studies already using CNNs on pictures of building, of the facade of the building, with like eight categories, like garages, residential, commercial, office. It attained global accuracy of around 60%. But I don't know if it's harder to train on true images, or if it's harder to train on made up images. So that's really the point where I have to determine when I must stop and be satisfied, and what I have to use to evaluate the quality of the model to be sure that I am not losing time, or I am not underachieving with the models.
Thank you. That's great. Do we have any more questions for any authors, please? Yeah, Geoffrey.
Yeah, I had a question for Giampiero, actually, the last speaker. I'm always puzzled to see that some cities are said to be too big somehow. So one of the results is, yeah, like Southern Napoli and others are too big for what they deliver in terms of production somehow, not productive enough. So I just wonder if you have any idea of why, because if they are too big, it means that there's still migration going on there. So there is some form of attraction. So what is it? So if we can go further than the model, what is it? Is there a specificity? Maybe, I don't know, it would be easy in France to say the southern city would be attracting more people because it's sunny. Probably in Italy, it's not the same case because it's sunny everywhere, maybe. But what is it that, what are the arguments we can put forward to explain that basically they're kind of oversized? Or is there something that we don't measure sufficiently well in terms of what means to be a productive or a good city in a way?
Well, I think that it's very difficult to reach a conclusion on this theme, and I think that a part of Italy is normal, has when the economic development is coupled with demographic growth of the cities, of various cities that are differentiated in space, because as I I have demonstrated there are a prevalence of medium-sized cities in Italy and a long history of this size. But there are many cities where are oversized respect their economic history, their economic situation. And I think that there are some issues, some questions that, for example, a classical zip law don't realize. And for example, the touristic movement and the touristic economies are a potential explanation of this differentiation. Another question is the silver economy, that is the growth of a person with more than 60 or 70 years old, and for this type of people, some cities are attractive despite the economic performance of the city in terms of production, innovation, creativity, and so on. So I think that these are two possible possibilities of the explanation of this question.
Great. Any more questions for our authors? Don't see any more hands. No takers. Okay. I think that concludes this session then. Thank you very much to the speakers and for the participants for coming along. I'd like to invite you all to come to the keynote talk from Luis Betancourt. That's at 5 p.m. UK time. So please do attend that. I'm sure it'll be a great talk. I'm sure we're all somewhat familiar with his work. And thank you once again, and see you later at some point in the conference. Cheers all.